Okay, I think I'm kind of live on YouTube at the moment. Let me know. Let me know in the chat if you are all doing well. I know probably most people for the GCSE part of this are not going to be watching live because you've all got your maths exam tomorrow and then you've got chemistry on Friday. But I'm still going to be here doing bits of GCSE initially, and then later on we're going to be going into some more A-level stuff from 8 o'clock onwards. So yeah, it'd be great to hear from people in the chat. I think I'm recording at the moment, which is good. Yeah, so a couple of things. The first one I want to mention, and I've put this in the live chat as well, hello Jamil, is if you are revising for GCSE chemistry, which I'm sure you will be, definitely tomorrow and tomorrow evening, there's a really good app that you should consider downloading. I used the biology one the other day, but if I had to revise for chemistry C1, I would be using this app. Now it's called Chem Quiz. I've just put a link, well I've just said what it is in the chat over here. And basically what it has is a huge amount of questions. So you can basically do maybe like a 10 question quiz. Let's do atoms, elements and compounds. So let me just put this down here. And this is just to show you really that although this is a mainly kind of physics live stream tonight, I'm still a science teacher and chemistry is still an important part of that. So yeah, the atomic nucleus has the same number of protons as neutrons. Always, never, or sometimes. I think sometimes would be the best answer for that. Which property or which subatomic particle determines the chemical property of an element? It's going to be, I reckon it's the electron, because that's the thing in the outer shells. What's the best way to separate a solvent from a solution? The answer would be chromatography. Oh no. A solvent from the solution. Filtration, no. There you go, simple distillation, easy. I should have got that right. Okay, but yeah, basically this is something that could be really useful if anybody out there is doing GCSE revision over the coming days. But yeah, let's just have a look in the chat. I'm not going to do much about A-level at the moment, but yeah, is there an app to revise physics unit 3 IAL Edexcel? Not yet, but I'm kind of working on one at the moment. So there's like an A-level physics online app kind of in the works, but it's just taking a lot longer. Yeah, people are scared for physics. Yeah, that's kind of normal. Yeah, people, I think if you're GCSE students at the moment, then you're well into the way of exams running, and actually you're kind of ticking them off. You've probably done history this morning, you did English on Monday. So if you're doing GCSEs at the moment, you're kind of really well into it. A-levels, I guess it's really coming up in the next sort of week or so, so I suspect you've got like another week of mass panic. But I will be here doing what I can, and don't worry about it. One last question from Jamil Rahman is, do you think we'll have an easier paper this year since 2023 was really hard? I reckon that it will be easier for AQA, especially compared to the 2023 papers, because I'm hoping that they've realised they've kind of messed up a bit. So hopefully they will make the papers easier. Okay, let's have a look at this question down here. So this question is a GCSE one. Maybe it's a little bit big. And it's about an LDR placed in series with a 4.24 volt battery and an ammeter. Draw the circuit symbol for the light-dependent resistor in figure 5 below. Okay, so the first thing we need to do is simply draw in the symbol for an LDR. Okay, I just realised I just need to do something on my phone. Sorry about that. Okay, so the first one is just the symbol for an LDR. So this is our light-dependent resistor. For that reason, the first thing I'm going to start with is the shape of a resistor that's kind of sort of connected into that circuit. Not the best drawn. That's probably pretty bad, isn't it? There's a circle around it, and if you do have your compass, that really makes drawing circles a lot easier. And then there's rays of light that come into it like that. So this is an LDR. Okay, right. The current measured on the ammeter is recorded as 2.6 MA. So what we have here is the lowercase m, which represents a milli. So that's going to be times 10 to the minus 3, so 1,000th of something. How long would it take for this amount of charge to pass through? So how long is going to be our time? So the first thing we have over here is I'm going to write down the equation Q equals IT. Now what it can be useful to do is maybe, if we know that that's a current, maybe just put maybe an I next to that, so that's the current. We've got the charge Q and we've got T over here. So what links Q, I and T? Well, Q equals IT. Again, this will be given to you when you're doing your GCSEs. It will be given to you in your data booklets. So then we can rearrange to say that T is equal to Q divided by I. Now the charge transferred was 0.52 of a coulomb, and the time that the current was 2.6 times 10 to the minus 3 amps. Okay, so we've got our charge in coulombs, our current in amps, and if we kind of just work this out, again, always relying on the calculator, this gives a lovely number equal to 200. So the time would be 200 seconds. So we've got some information here, but the tricky thing about this kind of question is that they've given you something with a unit prefix in front of that. Okay, so I'm just going to see what people are saying. Prem saying, after GCSE, should you start teaching yourself A-level physics and maths in the summer before you start year 12? Yes, definitely. I think that's a really good idea. You don't have to do much, but just a few bits and pieces. Obviously, I have videos that kind of cover all of that. I've got a workbook as well that you can do over the summer holidays that kind of prepares you for the start of year 12 physics. So that's something called the daily workout. Yeah. Ren asking, time in seconds, will they give you the unit? Yeah, they often give you the unit at the end. So it's a time in seconds. That's our standard unit. Right. How much energy would be transferred to the light-dependent resistor during this time? So this is, again, thinking about the amount of energy transferred. We know there's a certain time it takes. We also actually know that we've got a 4.25 volt battery in an ammeter. So what I'm going to do is just write on the circuit here that that's 4.25 volts. Okay. Now, one of the equations we can use to work out the energy transferred is, I think, probably one of the most tricky equations to do with electricity at GCSE, is that E is equal to QV. So we know the charge transferred is equal to 0.52 coulombs. And the potential difference across it, well, if there's 4.25 volts across the battery, the ammeter has zero resistance, and therefore there's going to be no voltage across that or no potential difference. And that means that whole 4.25 volts is all going to be across this component over here, and therefore that's times 4.25. So this question was tricky because the data you needed was right back at the beginning of the question all the way up here. So that's why it's a tricky one. Okay. So we can just multiply the two things together. And that's equal to 2.21. So I would give, because that's given to two significant figures, we could just write this as 2.2 joules. Okay, right, a couple of questions that people have said. Right, can a line of best fit be a curved or a straight line? Yes, it can be both. You can have curved lines of best fit as long as it kind of fits that data appropriately. I love conversation asking about can you do year 13 even if you fail one of your 3 AS levels? Often you can, but of course if you're, depending on how you fail, if it's just one subject, if it's by a lot, or if you just scrape an E, or maybe just or a couple of marks under the E, I think that's important to say. It's hard to say. It might be you've got extenuating circumstances, or it might be that you just haven't put enough work in. But I think this is the kind of thing where you've still got plenty of time to talk to your teachers now if you're in year 12 about what's going to happen at the start of year 13 if you don't do well. the best way to avoid that is just to do as much work as you can in year 12 to make sure that you get the grades you need to get onto the next part of your course. Okay, hopefully that helps answer some of your questions. Right, so we've got all that stuff, that's all good. The next question says, the potential difference across the LDR stays at a constant value. State and explain how the current in the LDR would change when the student increases the light incident upon it. Okay, so, right. Somebody's asking where you can get my daily workout book for after GCSE summer before year 12. Yeah, the best place to do that is if you go to I'm just going to put the link in. So anybody out there who might be thinking about doing A-level physics, I've put a link here called A-level physics on my website, which is alevelphysicsonline.com, and then it's intro to A-level. So that's just the link, and you can find it in the top banner of my A-level website. There's a link there to the book, and there's videos about all the different parts of A-level and how everything starts. Okay, right. So, cool. I love conversation. Yeah, no problem at all. Okay, so we've got some answer from Prem saying resistance would fall, so current would increase. So in this case, because the PD is constant. Yeah, we've got the next line there. So, so the PD across the LDR stays at a constant value. And again, I'm just going to do a little kind of diagram down here. So that's my LDR. Okay, there's light coming in onto it. If we were to think about what would be the potential difference across it, then that value of V is equal to a constant value. Okay. Now the other graph that I think is super important is this one here that looks at the resistance and how that changes with light intensity. Okay, sometimes measured in lux, but basically what happens is we have a graph for an LDR that looks like this. So this is the shape you need to know for an LDR. Okay, as the light goes up, the resistance goes down. So the question says, if you increase the light incident upon it, so the amount of light shining on it, so basically what we're going to do, we're going to increase the amount of light. So we maybe go from here up to this region. That means the resistance is going to go down. But of course we know that V is equal to I times R. And we want to look at what happens to the current. So we could basically take this equation here and say that the current is equal to V divided by R. Now that's going to be a constant value, and the value of R is going up, and therefore the value of I goes down. Is that right? So, sorry, when you increase the light on it, the resistance goes down. Sorry, the resistance goes down. And that means, because the resistance is going down and V is the same, when you've got a smaller value of resistance, we're going to get a much bigger value of current. Okay, so I think Prem's already said that. So basically, if state and explain how the current in the LDR would change, we can say that the resistance of the LDR would decrease with a greater light intensity. So the current would increase as V is constant. Okay, hopefully that's all right. Yeah, does that make sense? Hello, Alistair. Yeah, hopefully that's all making sense. So basically, even though that's like the main part of the answer, my working out was thinking, okay, that's the kind of a small bit of the circuit diagram. That's the kind of shape of the graph that shows the properties of this light-dependent resistor. And it's a case of if this goes up, then that goes down, which means that this goes up. Okay, next question then. We've now got a question, again, these ones here. I reckon if you've been watching my live streams, I know lots of you have been, it's good to see so many kind of familiar names back in the chat. I suspect that some of the questions that I've been going through will come up in your exam next week. Let's see what happens. Okay, so the first question is about looking at the way that energy is stored in the system. So this is the kind of a paper 1 topic for AQA, and it's going to be covered by all the other exam boards. What do we mean by the law of conservation of energy? Okay, basically energy cannot be created or destroyed, only transferred. To other stores. Okay, so this one here, pretty straightforward. Energy cannot be created or destroyed. I think that's kind of like the first mark up here. And then it can only be transferred to other stores. We might go from kinetic to gravitational, but effectively the amount of energy we start with in the whole closed system is going to be the same amount as the energy that we have at the end within that closed system. Okay, so we don't destroy it, it's just contained, as in like it's conserved. Okay, there's then an investigation where we've got a metal spring, it's attached to the wall, and they put a ball into that, and then they compress it, and then they release the ball. So basically what we're doing is we've got this ball here on the table, we compress the spring, and when you let it go, the ball goes flying out and the spring uncompresses. So let's think. The best way I think to do this is to think about the start and the end point of this. Okay, so the start is when the spring was compressed, the point was compressed. Okay, so basically this here is going to be my starting position. Okay, now the end position is actually a little bit further on when the ball has come to rest, so the velocity is equal to 0, and now the ball is in the end position of it not moving at all. So, what is the main energy store at the start of this? How is the energy stored initially? And I think that's probably a good way to kind of sort of begin kind of structure our answer. So let's just think about what happens before. Okay, we've got elastic potential in the spring, EPE in spring. Okay, so the first thing is before is we had, I'm going to call it EPE to show that this is the elastic potential energy. We've got the elastic potential energy in the spring. So that's kind of our before thing. Just reading a comment here from Raven saying, hello sir, you sat your IAL Edexcel Physics paper 2. So international students have already been in the middle of their exam process, and you did paper 2 today, and it went really well, so that's awesome. So Raven, I really appreciate you taking the time to comment on that, and yeah, I'm so happy it went well for you, and that my videos kind of helped you some of the way. So yeah, that's brilliant. Good stuff. Very good. Right, so that's before. What about the energy store at the end? Okay, so where's the energy stored at the end of this kind of thing that's happened? So initially, all stored in the elastic potential energy store. Where's the energy stored at the end? Okay, I'll just see what people put in the chat and we'll kind of discuss some of those things. But yeah, Alistair, Prem, some good answers so far. Okay, so basically what's happened is that at the moment, everything is still. So that means at this point, at the end, which is what we need to do when the ball comes to rest, there's going to be no there's going to be no kinetic energy because nothing's moving. And basically at the end, we've got the thermal store. And it's going to be the thermal store, this internal energy, and that's going to be the ball. It could be the table, it could be the air, and maybe potentially a very small amount in the spring. So basically we have the thermal store of all of these different things, okay? But there's going to be a point in the middle where once that spring has uncompressed, the ball is going to be moving, and that's where we have the kinetic store, okay? And for this question here, we don't have something which is moving up and down, so it's not changing its gravitational potential energy. Instead, the gravitational potential energy stays the same, but we go from elastic to kinetic to thermal. Okay, so in the middle part we have the kinetic store, and what we have is, as we go from this store to this store, the energy transfer process must be mechanical work. And the reason for that is that we have a force over a distance. So if we think about that spring, it's applying a force to the ball over a certain distance to accelerate it. And then, as the ball is going really quickly, it's got energy in the kinetic store, and that's going to be transferred to the thermal store, again by mechanical work, because what we have is a force, maybe due to friction between the ball and the table, or drag between the ball and the air, and there's going to be this force that's acting over a distance, and therefore work is done. Therefore energy is transferred because work is being done on it. So as I said, the kinetic energy is transferred to thermal due to friction. Yeah, which I think I can have answered as well. So yeah, exactly. So what we have here is we've maybe got the before, what it was like. We've got the after, and it's really important to kind of read the question thoroughly to work out what the start and end points are. We might talk about some of the energy transfers from one store to the other, and maybe some other intermediate stores within that process. Hopefully that's all good. Right. Okay, I think we've got some calculations. This time though, we've got a different experiment, much more like you'd expect, where there's something being flung up into the air. They use a catapult. It projects a ball vertically upwards. We've got the mass of the ball there. We've got the catapult can be modelled as a spring with a spring constant, so that's going to be K, and it's extended by a length of 0.25 metres, so that's the extension E down here. We then got a maximum height of 3.78 above its lowest position in the catapult. Okay, so basically from this point down here up to this point up here is going to be equal to 3.78 metres. Okay, so for this question here, we need to think about maybe which equations we're going to be using. And yeah, let's think about, first of all, let's work out the change in gravitational potential energy. Okay, so the change in gravitational potential energy is going to be mgh. Now the mass was 0.045. We're going to multiply that by the gravitational field strength of 9.8. And we're going to multiply that by the change in height, which was 3.78 metres. And when we do that, we get an answer of 1.66698. I'm going to leave that full display so I don't kind of round down too early. So that's going to be the change in this gravitational potential energy. How much energy, though, was put in from this elastic store initially? Well, the elastic potential energy is going to be equal to a half KE squared. So that's equal to 0.5 times the spring constant, which was 100, multiplied by the change in length, or the extension, of 0.25 squared. Okay, so 0.25, so that's 0.5 times 100 times 0.25 squared is equal to 3.125. Now effectively, that's the amount of energy in that we put into that system. So that's the amount of energy transferred to it as we're kind of pulling that spring down. And this here is going to be the amount of energy out. Now the efficiency, I'm going to swap colours here. The efficiency of something is the ratio, and it could be a number between 0 and 1, or it could be a percentage. The efficiency is the ratio between the energy out compared to the total energy in. So here the efficiency is equal to the energy out divided by the energy in. So the energy out was equal to 1.66698 divided by the total energy in, which was 3.125. And this is equal to 0.5334. But of course, our answer has to be given as a percentage. So 0.53 is the same as 53%. Okay, there we go. Now the last one, state the only force acting on the ball when it's at its highest point. So at this point over here, there's only going to be one force acting on the ball. So I reckon 75% of the people answering in the chat are going to get the correct answer. So what is the name of the force acting on the ball? What would be the best thing to write down in the exam? There's only one force acting on it. I'm going to tell you what it isn't. It isn't anything to do with air resistance, because at this point, when it's got to its very highest position, then there's going to be no air resistance because it's not moving. Okay, right, I reckon nobody's got the right answer so far. I think you'd all get the mark at GCSE, but I don't think, and again, we're thinking about what's the force, not the type of energy. So what, yes, here we go, we've got it. Stella, historical, Zruxi. Yeah, I reckon the best answer is weight. Okay, I know at GCSE sometimes they accept the word gravity, but I think to be sure of the mark, to make sure you don't lose that 1 or 2 marks, you know, throughout the paper, weight is the force acting on the ball at the highest point. Because there's this downwards force on this object that has mass due to the gravitational attraction of the Earth, and that's what we call weight. So weight is the correct answer, and although sometimes you see textbooks saying gravity, I don't think that's such good physics. Right, so hopefully people are learning something. I know they probably would allow it, Alistair, but you know, I want all of you to have no doubt that the answers you're writing down are going to be correct, and I want everybody who's learning physics to do it as properly as possible. So yeah, I just think yeah, weight is the best answer. Team Lethal, good stuff, weight. Okay, that was basically the end of the GCSE part here. Now, for some of you, you might know that I've been opening up these kind of Lego things, kind of often around this time at the end of the GCSE stream. Unfortunately, I've been a bit busy recently. I've not actually had time to go to Tesco's today, and I've run out of Lego minifigures. So the ones that we opened last week, I think that's one of my favourite, with the kind of sort of the EVA kind of spaceman or astronaut over here. We've got the kind of, actually you couldn't really see that because it's hidden on the table. We've got like the little kind of alien on holiday. There's quite a few other bits and pieces. So I've got these kind of things here. Unfortunately, I haven't got any more to open tonight, but that's what I'm aiming for. Maybe the space baby as well. So we'll see how it goes. But hopefully I can get back to the shop tomorrow and open some more of these. Also, people asking, why did I call this live stream about 7,000 joules? And this is kind of related to gravitational potential energy. So basically, if you look at the amount of gravitational potential energy, it's equal to the mass times the gravitational field strength times the change in height. Now, at the moment, my mass is about 93 kilograms. Okay, so I'd say about 42% of that is 42 kilograms of muscle, but I weigh about 93 kilograms. Plus at the weekend, I was out on a bit of a run, and I had about a 7 kilogram kind of rucksack, kind of backpack kind of thing for running. So that had water in it at times, and also included in this 7 kilograms, I reckon I've got like my shoes, the kind of the walking poles I was carrying. So I reckon my total mass is about 100 kilograms. Okay, and let's say we say G is about 10 newtons per kilogram. So that's kind of like the gravitational field strength. And over the weekend, I did a bit of a kind of a walk. I say walk, it was like a mountain marathon up in Snowdonia. It said 100 kilometers, but actually the distance was more like 110 kilometers when I actually measured it on my watch, with my GPS watch. And I went, you know, well over 21,000 feet, which is about 7,000 meters. So the total change in my gravitational potential energy over the weekend was my mass of 100 kilograms times G of 10 times 7,000. And when you do that, that's 1,000 times 7,000, which is equal to about 7 million joules. So yeah, I don't exactly know what that is in calories, but it wasn't just going up a nice smooth slope. But yeah, there we go. 7,000 joules was my increase and also decrease in gravitational potential energy over the weekend. Okay, unfortunately, Bramble, I'm not going to go over the things I said on Monday, but if you've already done that work, I can't remember which questions they were. You can find the answers for those on my website, probably on the pages to do with the daily workout. Yeah, hopefully that's all right. Sorry, Bramble. Right, should we do some proper A-level stuff? So I reckon it's about 8 o'clock now. Hello, everybody doing A-level. I probably suspect there's going to be more of you on the live tonight because you don't all have your paper 1 maths tomorrow and PB or RE in the afternoon. So yeah, I know lots of people had Edexcel exams today. So if you've done international A-levels today and you did paper 2, I really hope it went well. I know that some people have already said in the chat how well it went, and I'm so pleased that it's been going okay so far. And I guess you're kind of well into the exam kind of series of things happening now, and it's a bit more spaced out over the next couple of weeks. The stuff tonight is from this one here. This is one of my practice papers. You can buy it in my shop. This one is for an AQA 3A paper, and I would say that this one here is my gamma version. There's an alpha, beta and gamma. I've also put them into an exam pack if you are doing Edexcel or OCR, and including if you are doing international Edexcel A-levels, you might find the Edexcel pack, which is basically just the same questions in one big pack. You might find that really useful. Okay, so the first question we're going to look at is this one over here. So I'm sure a lot of you will have done something similar in classrooms. It's an easy practical for a teacher to run. So we're going to look at a way of determining a value for G. And in actual fact, a similar thing came up in my daily workout book on one of the other live streams that we did a couple of weeks ago. So they've got a red glass marble, smooth ramp to roll the marble down. We've got the length here. Describe how they could accurately measure the angle theta of the ramp from the horizontal with a ruler. So how would you, if you were having to answer a question like this in the exam, how would you actually measure the angle theta using a ruler? So that is the kind of the key thing to this. So trig, G3N Western, that sounds like a train. Yeah, trig is the right way of doing things. What you've got to think about is, you can measure maybe the distance from here over to here, and you can do that fairly easily. And then you can work out the height up to maybe where the ball is, or you don't even need to go to where the ball is. What you need to do is just have your ruler set up vertically like this, and of course to make sure it's vertical, that's when you have your set square. Okay, so if you know that you've got a set square there, we know that this angle here is going to be a right angle. This is A-level, and yeah, basically you don't need to know where the ball is, you just need to know the length, the horizontal length and the vertical height. Describe how they could accurately measure the angle theta. So you could, let me just get my answers. Basically, I'm just going to label this as well as that's decided O and A. So you could basically measure length A with a, I guess it says the ramp is over 1.5 meters. So you'd either use like maybe a tape measure rather than a meter ruler, because if you use a tape measure, you can make the distance longer than a meter. So we don't need, of course we could measure the length of the ramp, because if we know that's 1.500, we could just use that as a distance. Well thought out. We could measure the length A with a ruler, but we still need to measure height O with a vertical meter ruler, and then you need to use a set square to ensure it's vertical. Okay, I'm not going to spend too long on my handwriting, hopefully that's good enough. It's about just kind of putting down obvious things. We know that's going to be vertical, so anytime you have a height, in your answers when you're doing your A-level exams, put using a set square to ensure things are vertical. Okay. Right, people's questions. Right, there's quite a lot of questions coming in. What to do in the 9 days before the exam for A-level physics? I just think whatever you're doing, just keep doing as many past paper questions, and if there's things that you're not sure about or that you learn as you're doing the past papers, just add stuff to your own like flashcards. Keep looking at them all the time. Yeah. Yeah. Right. Sorry, I'm just going to hide some people. Okay. Right. So basically, use the set square to ensure it's vertical, and then you can talk about using trig to calculate theta. Okay, and that's going to be a much better way of measuring the angle rather than just trying to use a protractor. Because if you're putting a protractor against something like that, then you might get maybe within 1 or 2 degrees if you're lucky. The other thing you can do is often on your phones, if you're allowed phones in school, is there are apps that you can use that actually give you the angle that your phone is tilted at, so you can use it a bit like a spirit level, and that means you can put your phone onto the surface here, and then depending on the angle it will give you a digital readout. Okay, right. Okay, why should this give a low error in the angle measured? Basically, we're going to have a large distance measured, or large distances measured compared to the resolution of the instrument. So what we're talking about is, for example, maybe the height could be something like 700 millimeters plus or minus 1 millimeter. So what we're looking at is a big distance compared to a low error. Okay. Sorry, there we go. And the other thing is then you can say that this leads to a low percentage uncertainty. Okay, that's all it is. So basically what we want to do is we want to make sure that you have the smallest error possible, and also that that small error leads to a very, very low percentage uncertainty. Okay, so that one there, there'll always be a question, I'm sure, about how you kind of... oh yeah, so Holly, good question. Would the percentage uncertainty be smaller for a ruler compared to a protractor? Yeah, so for example, if you had a protractor, the angle might be 20 degrees plus or minus 1 degree, which would be equal to about 5%. Whereas if you had maybe a distance of 100 millimeters plus or minus 1 millimeter, and that's kind of like the lowest probably height you'd have, that's going to be an error of about 1% as a maximum. And as you go to a higher height, then that percentage error is going to go towards like kind of 0.1% compared to like having like a 5% error. Okay, good. Right, the next question then says, the student uses a meter ruler to measure a distance L of 1.5 meter along the ramp. They use a stopwatch to record measurements of the time taken. Calculate the mean time and the percentage uncertainty in this value. So the first one is just like a bit of simple data. But of course, in order to calculate the mean value for time, so I'm going to call it T with a small bar above it, what we need to do is add these up and divide by the number. But that's where you have to realise that they will give you anomalies and not tell you about it. So I would say that that is an anomalous piece of data, so you discard it. And that means the time, in terms of the mean value, is going to be 1.12 plus 1.08 plus 1.13 plus 1.14. And we're going to take whatever that number is and we're going to divide it by 4. Okay. Oh, people have got CIE tomorrow, have they? Okay, good luck, Light Arjun. I know you've been here in the chat many times. I know you're going to be absolutely fine. So yeah, best of luck tomorrow. Yeah, paper 2 and paper 5 for CIE. Yeah, I'd forgotten about that. So yeah, good luck. Hope it all goes well. Okay, so if you do that, we get an answer. Let's see, so we've got 1.12 plus 1.08 plus 1.13 plus 1.14 divided by 4 is equal to 1.1175. Okay, so I would say my mean time is going to be about 1.12. Okay, so I've kept that to the same number of significant figures as we have the data in the table. Now the percentage uncertainty, because we have repeated values, the percentage uncertainty is going to be equal to half the range divided by the mean value and then multiplied by 100. Because what we have here is multiple readings, and this is the way that you just have to work out the percentage uncertainty. Okay, is it just paper 3 stuff today, G3N Western? Yeah, it is kind of, but we're going to go back into like some CVAT questions. There's going to be, even though it's a paper 3 thing, and this is kind of more like a kind of practical skills thing, I know that these questions come up in all sorts of exams, and I will be doing some physics as well, but it's mainly that. Okay, so half the range. Well, the biggest number is 1.14, the smallest is 1.08. So that's going to be 1.14 minus 1.08 divided by 2. And that's equal to, I can do this in my head, but I'm just going to check, 0.03. And that's divided by the mean value, which I'm going to use as 1.1175. Then we're going to multiply it by 100 to get about 2.68. So that's 2.68. So about 2.7%. Okay. Right. Yeah, so we've discarded the anomaly. It's about 3% or 2.7. Again, I think I would say I found it best if you give your percentage uncertainties to 2 significant figures. I know it's kind of a bit, is it 1 or 2, but I think giving it to 2, you're not going to lose any marks. So people are asking some good questions. For diagrams in questions, Bramble, it always says it's not to scale, or do you have to just assume? Yeah, I would say that most diagrams are not to scale, it's just to kind of give you a bit of a picture. And I think it's quite rare they actually ask you to draw a scale diagram, but if they ask you to draw a scale diagram, then just, use your ruler and your protractor and compass if needed. Yeah. Right. But yeah, I reckon just most of the time, just assume that they're just like a rough sketch to kind of, just kind of try and represent what's being talked about in the question. Right. Somebody says that absolutely cooked, Bob. Need an A and you're at a C. Is it possible to jump 3 grades in 9 days? Yeah, it is. Because really, that's only jumping 2 grades, because you go from a C to a B, and then a B to an A. So it's only going up 2 grades, which is achievable. If you've got 9 days, that's over a week. That's a huge amount of time to make quite a bit of difference, and just learn the past papers, look at the questions that have come up. And if there's questions that come up that you can't do, they're the ones to really concentrate on. Okay, right. So, yeah, so half the range is the biggest minus the smallest divided by 2. So that's 0.03. And we divided that by the mean value, which we worked out up here, to give a percentage uncertainty of 2.7. Okay, calculate a value for the acceleration of the marble down the ramp. So this is where it's just a SUVAT question. And everybody watching this is basically going to be awesome at SUVAT, I know. Okay, so do we know how far it's gone? Well, it's gone a distance of 1.500 metres. So that's equal to 1.500. We know it starts initially at 0 metres per second. We don't know the acceleration, but we know the time because we've worked it out up here. Okay, so the time is equal to 1.1175. So again, I'm not going to use my rounded down value, I'm going to use my raw data. Okay, so the next part then is we need to think about, well, if S is equal to ut plus a half at squared, so that's the SUVAT equation that doesn't have a v term in it. U is 0, so that first bit is 0. So S is equal to a half at squared, and we want to work out the acceleration. The acceleration is equal to 2s over t squared. Okay, that's all it is. And then we just need to put some numbers in. So the 2 times s is going to be 2 times 1.500, and then our t is 1.1175 all squared. So this is just an easy couple of marks. Okay, yeah. By the way, if I don't answer everybody's chat and everybody's kind of question in the chat, I am sorry, because I can see there's like a lot coming up quite quickly, and I know that what's really nice is that people are talking to each other and helping each other out. So yeah, I'm afraid that I can't answer them all in the actual live stream, but do keep helping each other out. There's some really good advice going down there. And don't burn yourself out. You've got loads of time, and it is difficult that you don't just work too hard, because sometimes you get decreasing returns the more time you spend doing something. Okay, so to work that out, that's just going to be equal to 3 divided by 1.1175 squared, which equals 2.4. So the acceleration would be 2.40. And I reckon that's an appropriate number of significant figures. So we've got really 3 significant figures for the time, 4 significant figures for the distance, so we can give that 3 significant figures. And then we want to calculate a value for the uncertainty in this acceleration. Now, for this, I'm just going to use my own kind of way of kind of showing this. We want to look at the percentage uncertainty in the value of the acceleration, and that depends on the uncertainty in s and the uncertainty in t. So that depends on the uncertainty in s, which I'm going to put as a percentage symbol in an s, plus the uncertainty in t. But here what we've got are our values of t squared. So we've got to have 2 times the percentage uncertainty in t. Okay, so so what we're doing is we're going to be looking at the percentage uncertainty in s. Now, do we know that? Well, it says here they've used a meter ruler to measure the distance of 1,500. Now, that 1,500 is a single value, and to work out the percentage uncertainty in this, it's going to be equal to the resolution of that instrument, which is 1, divided by the measured value, which is 1,500, and then we're going to multiply that by 100, which equals, is that right? 0.0, so sorry, 1 divided by 150. So that's equal to 0.66667%. Okay, is that all right? Okay, so yeah, so basically this is the uncertainty in s, and we're going to add that to 2 times the uncertainty in t, which we worked out here as about 2.68. So to work out the percentage uncertainty in a, it's going to be equal to 0.6667 plus 2 times 2.68. And when we do that, that's equal to about 6.02, I think, if that's right. Have I made a mistake somewhere? That doesn't seem right. Okay. Cool. Okay. So that's about 6%. Okay. And then what we need to do is find about 6% of the acceleration. And the acceleration was 2.40 meters per second. And we need to multiply that by 0.06. And that's about 0.014. So the uncertainty is about plus or minus 0.14 meters per second. Okay, so what we did for this one here is that the approach we took was we knew the value for the acceleration. If we worked out the percentage uncertainty in s, and we added that to 2 times the uncertainty in t, we could then look at the total percentage uncertainty in the acceleration. And if you know the percentage uncertainty in the acceleration, we can multiply it by the value for the acceleration to get the actual uncertainty in that value. If you add or subtract two values, you add the substitutes. Yeah, I think that's right. Okay. Sorry, I'm just going to check one thing. Okay, cool. Right. We then need to start with this question over here. Add arrows to figure 2 to show the weight acting on a mass on the ramp and also the component of weight acting down the ramp. Use the component of weight parallel to the slope to write an expression for the expected acceleration down the ramp. So for this one, again, this is kind of like a kind of a paper 1 kind of style question. So let's think about the ball. There's going to be a weight force acting vertically down. Okay, now that is going to be at an angle to the slope equal to theta. So if that angle there is theta, this angle here is theta as well. And there's also going to be a component of this weight which is going to be acting parallel to the slope like that. Okay, now the weight is equal to mg, and that means that component of weight parallel to the slope is equal to mg sine theta. Okay. Okay, so basically that's the force down the slope. Now it says use a component of weight parallel to the slope to write an expression for the expected acceleration down the ramp. So that's the first thing. It's just kind of like a free body diagram, label stuff, and I would urge you to do this with a ruler, a pencil, and a protractor in the exam, and maybe then go over it in pen. We can say that the force is going to be equal to the mass times acceleration of that object. Now the force causing it to accelerate is this force parallel to the slope. So that's equal to mg sine theta, and that's going to cause this mass to accelerate. Now what we then have is we have a mass on this side and a mass on that side, so they cancel. And that means we can say that g sine theta is equal to a. Okay, so that's how we'd work out the acceleration. The acceleration is going to be equal to g sine theta. Okay, now it says here that the ramp the student used was inclined at an angle of 16 degrees. Use your expression from part 1.6, so that's this one over here. And that's what they'll often ask you to do. They'll often ask you to show something, and then you use that for a later part of the question. And we're going to use the acceleration from part 1.4, which was equal to... the acceleration from part 1.4 was equal to 2.40 meters per second squared. And we're going to calculate the percentage difference between... we're going to use that to find a value for the acceleration due to gravity. And then... it is a smooth slope. It is, yes, Holly. Yep. We're going to find that value of g and how that compares to the actual value. So the first thing we're going to say is that the acceleration is equal to g sine theta. And we want to find the value of g, which is equal to the acceleration divided by sine theta. Now the value for the acceleration was equal to 2.40 meters per second, and we're going to divide that by sine of 16. So that's the slope. Okay, and this basically comes from this part of the question that we had up here. And that means g is equal to 8.71 meters per second squared. So 8.71. Okay. So that's the experimental value for the gravitational field strength. Thank you, Maria. So what is the percentage difference? So this is something that doesn't always come up that often, but I still think it's something that you need to know about. Basically the percentage difference in an answer So the percentage difference is equal to maybe the real value or the accepted value or the true value, which in this case would be 9.81. Take away the experimental value. So it's going to be the difference between these two things divided by the real value. And often we kind of put the modulus symbol there to kind of just have the positive value of that, and also multiply that by 100. So in this case, the real value is 9.81. The experimental value was 8.71, and we divide that by 9.81 multiplied by 100 to get an answer equal to about 11.2. So the percentage difference is about 11.2%, or you could just say, I suppose because we know the angle is 16 degrees, that's only two significant figures, we could probably only really give each of these to maybe one significant figure, sorry, to two significant figures, so maybe 8.7 meters per second and 11%. Okay, so yeah, basically that's the percentage difference between your experimental value and the true value. Okay, I think that's kind of like the end of this bit of physics. If you want to get your own copy of this to work through, then you can find it over in my shop. You can find it probably linked underneath this video. Right, so let's see what some of the people's questions are. Bob says, do I have videos on the space and thermodynamics topics? Yes, Bob, I've got videos across everything for A-level physics, including all the year 13 content. In fact, what I will do, I'll just put up a link in the chat that you can find all of this on. Basically, I've got my, it's probably not as full as it probably could be, and there's probably more stuff I haven't quite put on there yet. But basically, Bob, that's for you. That link that I've just put up in the chat for those watching live is my full video list over at A-Level Physics Online. So I've got anything to do with space and astronomy and telescopes and things like that, as well as all the kind of stuff to do with thermal physics. So hopefully that can be helpful. Something that Bobia says about in the beta paper related to the minimum amplitude of a sphere rolling on a track. How do you find that? Let me just see if I can find that question. Sorry, just one sec. So this is a question. Okay, yeah, so I see what you mean. Let me just see if I can answer your question. So, yeah, so Bob's saying, no, sorry, Bajar saying, is there something I didn't understand in relation to the minimum amplitude of a sphere rolling on a track? How do you find that? Yeah, so for this one, have I just frozen? Am I frozen at the moment? I think my cameras have just frozen. Can anybody hear me out there? Am I frozen? Right, okay, so okay, right, I reckon my cameras have gone. I think they're just telling me it's time to go because it's 8:30. So you can hear me, which is great. Just ignore whatever. I guess I can change screens. So just imagine my lips are moving. Badger, tell you what, if you send me an email to hello@physicsonline.com, which is like the one you can find on my website, I'll answer your question about the paper, the beta paper, and the question related to the amplitude of the sphere rolling on the track. So yeah, send me an individual message. You can do that to hello at physicsonline.com. And yeah, for the rest of you, I'll hopefully be back again tomorrow with cameras working, and I'll see all of you then. Well done for everybody who's done exams so far. I've decided probably not to do the crash course this year, Bramble, just because I think it would be a bit too rushed, but I'll probably do them next year and maybe a bit more group tuition throughout the year. Yeah. Okay, good night everybody, and I'll see you tomorrow. Thank you.